Welcome to Module 17, Building Envelope, Moisture, and Condensation. In this module, we move outside the air handler and look at the building itself. The HVAC system conditions the building, but the envelope determines how the outdoor environment reaches it. We will connect heat flow, air leakage, vapor movement, dew point, and condensation risk to practical BAS decisions. The goal is not to make every BAS technician an envelope engineer. The goal is to recognize when a comfort, moisture, or condensation complaint is not just a set point problem. Here are the learning objectives. You will learn how the building envelope manages three flows: heat, air, and moisture. You will separate moisture paths because bulk water, vapor diffusion, and air-transported moisture are not the same problem. You will use dew point and surface temperature to evaluate condensation risk. You will recognize thermal bridges and perimeter load patterns. Most important, you will learn how BAS trends can support a building science investigation without turning every envelope defect into a control sequence debate. This roadmap follows the way envelope problems appear in the field. We start with the envelope as the environmental separator, then move through heat flow, thermal bridges, air leakage, moisture transport, condensation risk, barriers, solar gain, BAS monitoring, worked examples, and a practical assignment. Keep the central idea in mind. The BAS can reveal patterns and reduce consequences, but physical defects require physical repair. Avatar narration. This visual shows the three paths we need to understand: heat, air, and moisture. Heat moves through the assembly. Air can leak through gaps, joints, doors, roof penetrations, shafts, and discontinuities. Moisture can move as bulk water, vapor, capillary action, or moisture carried by airflow. The BAS monitoring panel shows useful evidence: indoor temperature, humidity, dew point, surface temperature, and pressure differential. The lesson is that condensation risk is not just a temperature problem. It is a heat, air, and moisture problem. Production notes. Use this as a full-screen teaching visual. The avatar should walk across the major paths and monitoring panel. The envelope is the environmental separator. It separates indoor conditions from outdoor conditions. It includes the obvious parts, like walls and roofs, but also the less obvious parts: joints, penetrations, door seals, window frames, foundations, and transition details. In BAS work, the important question is not only whether the equipment can heat or cool. It is whether the building is leaking heat, air, or moisture faster than the system can manage. Heat moves through assemblies by conduction, convection, and radiation. The simplified relationship Q equals U times area times temperature difference is useful, but it is only a screening estimate. Real buildings include thermal bridges, air leakage, moisture, wind, solar radiation, insulation gaps, and framing effects. If a calculation uses only nominal insulation value, it may miss the whole assembly behavior. A thermal bridge is a path that conducts heat faster than the surrounding construction. Examples include metal framing, slab edges, window frames, fasteners, shelf angles, and structural penetrations. The BAS may show the zone temperature near set point, but occupants near the perimeter may still feel cold or hot because local surface temperatures are different. This is why averages can mislead us. Air leakage is driven by pressure difference, wind stack effect, mechanical supply and exhaust imbalance, door operation, shafts, and envelope discontinuities all matter. Air leakage is not only an energy issue. Air carries sensible and latent energy. In humid climates, infiltration can bring moisture into the building. In cold climates, exfiltration can carry indoor moisture into cold assemblies where it can condense. Moisture can move as bulk liquid water, vapor diffusion, air-transported moisture, and capillary action. These are different problems. Lowering humidity may help one condition, but it will not repair a roof leak. Adding a vapor retarder does not automatically stop air leakage. This distinction matters because the corrective action must match the path. Condensation risk is one of the most practical places where BAS data supports building science. If a surface temperature is below the adjacent air dew point, condensation can occur. The BAS may compare room dew point to a chilled pipe, radiant surface, chilled beam, duct, or window frame, but the margin must account for sensor accuracy, location, air movement, and hidden surface conditions. A 2-degree margin may not be enough. A vapor retarder limits vapor diffusion, an air barrier limits airflow. One material can sometimes contribute to both, but the functions are different. Placement depends on climate, indoor conditions, assembly type, and design strategy. BAS professionals should understand why humidity or pressure changes affect moisture behavior, but we should not prescribe envelope assemblies without appropriate building science expertise. Windows transfer heat by conduction and solar radiation. Solar gain depends on orientation, time, shading, glass properties, and weather. A west-facing office that overheats every sunny afternoon may have a zoning, solar, or sensor placement problem. The BAS can help by comparing trends by orientation, integrating shading where available, adjusting schedules, and applying reset limits, but the root cause may be envelope and zoning. BAS trends are powerful, but they are not magic. Useful points include indoor temperature and humidity, dew point, surface temperature, building pressure, outdoor temperature and humidity, wind, solar conditions, and alarm response. The BAS manager helps by organizing evidence, showing timing, comparing zones, and identifying whether conditions line up with weather, occupancy, pressure, or equipment operation. These examples show how to use simple checks. A wall heat transfer estimate gives a starting number, but it excludes air leakage and solar effects. A pipe surface 2 degrees above room dew point has very little safety margin. A west-facing perimeter complaint may be about solar load and zoning, not controller tuning. The calculation is not the final answer. It helps identify the next evidence to verify. Here is a realistic field scenario. A laboratory ceiling developed condensation during humid summer weather. Cooling coil performance was adequate, so the coil was not the main problem. The investigation found that exhaust had increased without matching outdoor air, and the building operated negative. Humid outdoor air entered through roof and wall leakage and contacted cold surfaces. The solution required correcting pressure balance and envelope defects. The lesson is clear: do not turn every envelope problem into a set point debate. This slide brings the module into a field checklist. Common mistakes include using nominal insulation value as whole wall performance, ignoring thermal bridges, confusing vapor retarders and air barriers, assuming condensation is only caused by low temperature, and using HVAC capacity indefinitely to compensate for air leakage. The checklist helps structure the response. Document location and orientation, review outdoor conditions, trend pressure, compare dew point to cold surfaces, inspect leakage paths, rule out bulk water, and involve building science expertise when needed. The best answer is B. Condensation at a diffuser is a dew point and surface temperature problem. Before changing the temperature set point, verify room dew point, diffuser surface temperature, airflow, humidity, sensor location, outdoor air moisture, and pressure conditions. Lowering the temperature may make the surface colder and could make the condensation problem worse. For the assignment, choose one real or sample envelope related complaint and build a structured review. Document the location, orientation, weather, indoor temperature and humidity, building pressure, dew point, surface temperature, and likely heat, air, and moisture paths. Then recommend one safe next test or investigation step. The key takeaway is that the BAS can manage loads, reveal patterns, and support decisions, but it cannot erase the physical pathways that create envelope problems. Next, we move to building pressure and critical spaces.